course, Organic Contaminants in the Subsurface Environment. Is our presentation with the Waterloo people, with some help, great help from Massimo, John Molson, and Marco Petitta, and myself. It's been a pleasure offering you this course again. Well, I'm going to present you free and residual phase relationships. You have to be careful and pay attention. These are very conceptual subjects that are going to be shown to you, and you have to look closely to each movie that we're going to present. So I strongly recommend you to look closer and go back and forth several times until you do get the concept right on your head. Okay? It's very important so you can understand how free phase and residual phase behave when you're dealing with subsurface contaminants that are immiscible or partially immiscible with water. I'm Professor Everton de Oliveira from Hidroplan. I work at UNESP in São Paulo, University of Waterloo, Canada, and I'm also a member of the Brazilian Groundwater Association and some other associations like National Groundwater Association and International Hydrogeologists Association. Okay. And here are my contacts. If you want to reach me, please feel free to do so should you have any doubts about this course. Reference, we have a few, and those are the ones that show you some basic of the theory that we're going to see. Okay, you can go through and use these as you wish. First, I would like you to take a close look at the form, at the shape of the droplets that we have here in these pictures. I amassed quite a few of these pictures so you can actually have a good feeling of the shape of the droplets on top of a surface. Most of these droplets look like water, but maybe not all of them are water. And the relationship between the liquid and the surface is the main point that I want you to observe through this picture. If you take a look at this, it looks like the liquid doesn't want to touch the surface. The surface looks dry. Okay? We have some others like this one here where apparently the liquid does want to cover the surface. Look the difference from this droplet and this long one, or this one. This is much flatter than this one here. It's bulgy. Okay? Look at that one. That's not as good to cover the surface as the previous one. Or this one's here. Look. It looks like they're barely touching the surface, right? They're touching the surface a bit. It looks like they don't want to touch the surface clearly. Look at this. Same thing. Some of them want to cover the surface. It looks like they want to cover the surface. Some others are just very touching the minimum. Looks like the area that is touching the surface is the minimum necessary to keep it on top of it. This one here looks like a ball. It doesn't touch a huge area on the surface of the leaf. Look at that one. That's of course is photoshopped, but it's the same idea. This other one here is a bit of an exaggeration, but it looks. You see? That one is more realistic, but still we can see that it barely touches the surface. That's the minimum area that could touch the surface to hold the weight of the liquid, and the shape is determined by that. And that's the same here. This is very good to see. Look at the shape and all that. Look. Nice, this picture. I love this picture. Look at that. So it looks like the balls in the area where they touch the surface is so small compared to the size of the droplet. look at this. In feathers, you see that ducks look dry when they swim, and you can see that the water doesn't want to touch. So the shape of the droplets matter. Okay, the shape of the droplets matters much when we see this relationship. And I want to talk about that in detail for you in this class. Okay, so you see the shape of the droplets there. Look at that. How droplets form as it drops, as it's dripping to the floor, for example, by gravity. The shape of the droplet is very important, and we're going to talk about that later. Well, now we have here an interesting view for you to understand, or actually this is more to motivate you to understand the concepts that we're going to use in this class. What we have here is a free phase. We have a free phase plume on an old refinery. And I want you to pay attention in two things here. Here we have the groundwater elevation in feet. See, groundwater elevation is going to vary along the time. Time is going to pass here. I want you to pay attention at this point here, the groundwater elevation and the shape of the plume. Of course, as I mentioned previously, I do recommend you to take a good look at this video and go back and forth several times until you realize what the relationship between the groundwater elevation or the groundwater variation and the shape, the size of the plume. Okay? Take a look at that. I'm going to release the movie and you take a look. Groundwater elevating. Moving downwards, lower, higher, and take a look at the shape of the plume. If you're free to watch over and over this movie, take a look. Big plume disappeared. Wow. Now it's reappearing again. Oh, big. Well, disappeared again. And it reappears later as the water table goes down. So, there is a repetition here, and I do want you to take a close look at that. As the water table elevates, the plume tends to shrink. As the water table goes downwards, the plume tends to be larger in size and thicker in thickness. So you have to be very careful and watch that movie several times, because when you're going to show you the effects of groundwater elevation and how it happens in a porous media, you have to relate back to that situation, because that's what you're going to see in a field situation where you're dealing with free phase and residual phase. Okay, so this is our introduction, is our first class. Thank you, and I'm going to show you next concepts in a few moments. Thanks.